Hello, dear subscribers and viewers of the channel. Today, we will talk about the history of astronomy and its development. Astronomy is a science that studies the motion and properties of celestial objects such as stars, planets, and the moon based on observations made by humans. It is one of the oldest sciences and has both ancient and modern roots. Astronomy has evolved in different ways in different cultures and civilizations, and today I will tell you about some of its achievements. One of the cradles of astronomy was Mesopotamia, a region between the Tigris and Euphrates rivers, also known as the cradle of civilization. Systematic observations of celestial bodies began there about 5,000 years ago when the Sumerians started to study the starry sky. Observations of celestial phenomena and the development of astronomical knowledge went hand in hand with the religious beliefs of the Sumerians. They made significant contributions to the field, including developing the first known calendar system based on lunar cycles. The Babylonians determined the months based on the phases of the moon, making it possible to coordinate agricultural work and religious holidays. Creation of the first star charts. The Babylonians knew the exact dates of the summer and winter solstices by observing and recording the movement of the heavens for astrological purposes. They had a unique view of the solar system with 12 planets, each closely associated with a specific deity. The sun Utu, Shamash, was the central deity, the source of light and heat, while the moon Nanna Sin represented nighttime lighting and timekeeping. Mercury Nabu served as the messenger god and keeper of knowledge. Venus Inanna, Ishtar was the goddess of love and war. Earth Ki was worshipped as the mother goddess, and Mars Nergal was the god of war. Jupiter Marduk was supreme god and conqueror of chaos, while Saturn Ninurta was god of agriculture and hunting. The Sumerians included several planets that were invisible to the naked eye in their solar system: Uranus, Neptune, and Pluto. These planets were considered to be the gods of the heavens, each with their own unique roles and responsibilities. Nibiru, or Planet X, played a significant role in Sumerian mythology and cosmology. This planet was believed to appear periodically in the sky and hold a special place among the other gods. The Sumerians' understanding of space and their ability to observe celestial bodies was impressive, as evidenced by their creation of ziggurats, which were stepped temples observatories. The Babylonians later inherited this knowledge and further developed astronomy, creating accurate methods for predicting solar and lunar eclipses and dividing the sky into zodiac signs. The modern system of measuring angles 360 degrees in a circle also originates from the Babylonians. The calendar based on lunar cycles became the prototype for many modern chronological systems. The principles of astrological forecasting laid down in Mesopotamia have been preserved until today. Astronomy and religion were inextricably linked in the ancient world. Celestial bodies were considered manifestations of divine forces, and knowledge of their movements was essential for conducting religious rituals, predicting the future, receiving the favor of the gods, and coordinating public life. The methodology of ancient astronomers laid the foundation for a scientific approach. They used systematic observations, fixed the results, searched for patterns, created mathematical models, and formulated predictions. Ancient astronomical achievements continue to influence modern science, including principles of time measurement, coordinate systems, methods for astronomical observations, mathematical calculations, and understanding celestial phenomena. In ancient Egypt, astronomical knowledge and cosmological concepts were closely linked to the culture and beliefs of the civilization. Some of the main achievements of the ancient Egyptians include creation of a solar calendar, which consisted of 365 days divided into 12 months with 30 days each, with 5 extra days added at the end of the year to make up for the remaining time. Orientation of pyramids and temples using stars. For example, the Great Pyramid of Giza was aligned with the cardinal points, and temples such as the Temple of Amun-Ra and Karnak were designed to allow the sun's rays to illuminate statues of deities on specific days. Development of star maps, which were used to determine time at night by tracking the movement of 36 constellations known as decades that rose and set every 10 days. Astronomical texts and predictions. The Egyptians produced many astronomical texts, including the Book of the Dead and the Book of Heaven. These texts described celestial phenomena and their connections with religious beliefs and were used to predict eclipses, planetary events, and the timing of the Nile floods. Famous Egyptian astronomers, the priests of the temples of Mer-Unnut and Emi-Unnut were observatories that conducted astronomical observations and interpreted the movements of the stars and planets. Ancient Greek astronomy. Astronomy in ancient Greece introduced the first concepts of space and made significant discoveries that formed the basis for modern science. Early concepts of the universe included Anaximander's geocentric model. The Earth is stationary at the center of the universe, with stars and planets orbiting it on a celestial sphere. The theory of Pythagorean music. Celestial bodies moving in circular orbits emit sounds that create harmonious music from the heavens. Aristarchus' idea of the heliocentric solar system. The sun is at the center and planets orbit around it. Ancient Greek scientists sought to understand the laws of the cosmos and developed fundamental concepts. Some of their contributions to ancient Greek astronomy include Eudoxus of Knidos founded the first observatory and a school with an astronomical bias, establishing theoretical astronomy as a field of scientific knowledge. Hipparchus of Nicaea developed the first star classification system and introduced concepts like orbital eccentricity, apogee, and perigee. He also discovered Earth's axial precession. Aristarchus of Samos was an ancient Greek astronomer, mathematician, and philosopher who is credited with founding the heliocentric model of the solar system and explaining the rotation of the Earth as the cause of day and night. His work laid the groundwork for new mathematical techniques that have been used in astronomy ever since. The Romans adapted Greek astronomical ideas and incorporated them into their culture. Claudius Ptolemy's Almagest was a significant source of knowledge for the Romans, describing the movements of the sun, moon, and stars in relation to Earth. Practical observations in ancient Rome also helped determine seasons and aid navigation. These cosmological concepts from Greece and Rome form the foundation for modern astronomy. Ideas about the spherical shape of Earth, developed by Greek scientists, became the basis for later theories about the universe's structure, as well as instruments such as the astrolabe and armillary sphere, which were invented by the Greeks for observation. The Maya civilization attached great importance to astronomy. This is evident from numerous archaeological discoveries at the sites where the cities of the Maya were located. Ancient Maya astronomers were able to predict eclipses and carefully observed various astronomical objects, including the Pleiades, Mercury, Mars, Jupiter, Saturn, and the North Star. They accurately determined the synodic periods for all 5 planets, with Venus being especially revered. The Maya calendar was based on a 20-day month and a 13-day week, and its beginning dates back to 1738 BC. Their chronology began in 3113 BC, and they gave proper names to constellations such as Rattlesnake Rattle and Turtle. They believed that the movement of planets and stars influenced earthly events and associated celestial bodies with gods. Remnants of cities and astronomical observatories are impressive. The 13-meter-high Karakol Observatory in Chichen Itza has a domed roof with small windows, and its spiral staircase gives it the nickname of Snail Tower. The observatory in Palenque is a complex of buildings and a tall square tower. Incan astronomy was closely linked to cosmology and mythology. Each sacred place, known as a waka, corresponded to a celestial body or natural phenomenon. This connection is reflected in legends that tell of celestial beings descending to Earth and emerging from rocks, caves, or springs. According to Incan beliefs, people themselves came from these places. The most important celestial object was the Milky Way, which was seen as a river Mayu where all other significant bodies were located. Its position in relation to the Earth's rotation marked the boundaries of 4 sectors of the world. Two main avenues and roads intersected at a similar angle, along with irrigation canals. The Incas were aware of the difference between stars and planets. They observed Venus, Jupiter, and Saturn, but there is no information about their observations of Mercury and Mars. Their names for the planets suggest that they were aware of Jupiter's Galilean satellites and the atmospheric fuzziness around Venus. They used stones or pillars to measure the position of the sun. 2 stones were placed east of Cusco, and 2 more were placed west. When the sun passed through these markers, it marked the beginning of summer or winter. The winter markers were named Pukui Sukanha, and the summer markers were called Chirasu Kenka. Jose de Acosta mentioned 12 stones, which he called Sakanga, and Antonio de la Calancha mentioned 8 stones on the east and 8 on the west. It seems that as early as the middle of the 16th century, after the Spanish conquest, the pillars in Cusco were abandoned and surveillance over them ceased or became less strict. Astronomy in other countries in Europe, the Druids of Celtic tribes undoubtedly had some knowledge of astronomy. There is evidence to suggest that Stonehenge was not only a place for rituals, but also an observatory built around 2000 to 1500 BC. Ancient Chinese astronomers identified constellations, described the Milky Way as an unexplained phenomenon, compiled lists of stars and their coordinates, and created catalogs. To accomplish this, they built special towers for stargazing, which were ancient observatories. Observations of the sun allowed the Chinese to refine their lunar calendar and create sundials. In addition, astronomers of that time were able to observe and describe a phenomenon that is now known as sunspots. In 355 BC, astronomers Gan Gong and Shai Shen compiled the Star Canon of Gan and Shai, a consolidated catalog that included over 800 stars, presumably the world's first star catalog. Astronomer Zhang Heng 78 to 139 BC divided the sky into 120 for constellations and estimated there were about 1,500 stars visible in China, naming 320 of them. At the end of the 1st century AD, astronomer Jia Kui developed new instruments for measuring the coordinates of celestial bodies, including the ecliptic theodolite. Ancient Chinese astronomy left a significant impact on world science, with many of their observations and predictions later used by scientists in other cultures. The accumulated knowledge in China became the foundation for the development of astronomy in other parts of the world. Ancient India made a significant contribution to the development of astronomy. The knowledge about celestial bodies and their movements was used to calculate the time for religious ceremonies, plan agricultural work, and create calendars. The idea of the Earth rotating around its axis was proposed by the Indian astronomer and mathematician Aryabhata in his work Aryabhasya. He explained the apparent movement of stars and planets in the sky. Aryabhata pointed out that eclipses happen because the Earth blocks the light from the Sun from the Moon lunar eclipse, or the Moon blocks the Sun from Earth solar eclipse. Aryabhata and other Indian astronomers developed precise astronomical tables that detailed the positions of the planets, the dates of eclipses, and other celestial events. Aryabhata, in his Sanskrit astronomical treatise, Surya Siddhanta, calculated the length of the solar year to be 365.3586805 days, which is close to the modern value. Indian astronomers used simple instruments such as Sharira, an angle measuring device, and graduated circles to carefully record the positions of stars and planets, creating astronomical tables and maps. The knowledge of these ancient Indian astronomers influenced the development of astronomy in other cultures, and their methods and tables were later passed on to Arab scholars, who in turn transmitted them to Europe. This played a significant role in the evolution of medieval astronomy. Many mathematical and observational techniques that originated in ancient Indian astronomy continue to be used in modern astronomical research today. The astronomy of the Sassanid Empire, which existed from 226 to 640 to AD, developed in a context that combined Zoroastrian astrological traditions with those of Greece and India. One of the most significant developments was the creation of Zijisha, a state work on astronomy and astrology written around 50 AD and revised during the reign of Khosrow I Anushirvan 531 to 579. This work combined Zoroastrian beliefs with Hellenic and Indian influences, and another important aspect was the development of an astrological approach to history. Additionally, the establishment of observatories in Persia allowed for systematic observation of celestial events such as solar and lunar eclipses. The use of astronomical instruments like the astrolabe became common. These tools were used to calculate positions of stars, the sun, and determine times of sunrise and sunset. Astronomy and cosmological concepts in the Sasanian state were linked to Zoroastrian myth. Constellations, their images, roles, and Persian representations were intertwined with religious symbols. They embodied the struggle between light and darkness, order, chaos. The Sassanids maintained Zoroastrianism as state religion but incorporated mythical images and symbols in their astronomical knowledge. Arabic astronomy developed from the 8th century to the 15th century, drawing on ancient Greek astronomy as its main source. It also drew on early Indian astronomy and the astronomical knowledge of the Sassanid Empire, which was centered in modern-day Iraq and Iran in its early stages. The writings of Islamic astronomers were written in Arabic and can be considered an international language for medieval science. This is why Arabic astronomy is also known as Islamic astronomy. Not only Arabs, but also people from other cultures in the region contributed to this development. The 7th century, the beginning of contact with astronomical knowledge from the Greeks and Indians. Under Caliph Omar I's order, the Arab Caliphate developed a lunar calendar based on religion. In the 8th century and the first half of the 9th century, there was a period of intense translation of scientific literature from India and Greece into Arabic. Al-Ma'mun, the caliph at the time, was the main sponsor of scholars, and he founded the House of Wisdom in Baghdad as well as two observatories for astronomy in Damascus and Baghdad in 820. During this period, prominent astronomers like Ibrahim al-Fazari, Yaqub ibn Tariq, Habash al-Asib, Muhammad ibn Musa al-Khwarizmi, Umar ibn al-Faraj, Abu al-Wafa al-Batani, Thabit ibn Qurra, and their students made significant contributions to astronomy and mathematics. They discovered changes in the inclinations of the ecliptic and equator, as well as precession. During this time, scholars also achieved complete mastery of the mathematical tools used in Greek astronomy, particularly the theory of Ptolemy. The second half of the 9th century to the end of the 11th century was the heyday of Arabic observational astronomy. During this period, prominent astronomers such as Muhammad al-Batani, Abd al-Rahman al-Sufi, Abu Jafar al-Hasan ibn Ali al-Haytham, Abu al-Wafa Muhammad ibn Muhammad al-Buzyani, and Abu al-Hasan Ali ibn Abd Allah ibn Yunus Avicenna made significant contributions to astronomy. They discovered the motion of the apogee of the sun's orbit relative to fixed stars and equinoxes and began to develop theoretical understanding of celestial motions. These discoveries led to first doubts about geocentric universe model, where Earth was believed stationary. The 13th and 14th centuries saw a search for new theoretical foundations in astronomy as the Ptolemaic system of epicycles was challenged by inconsistencies with physics. This led to what is known as the Andalusian Revolt, in which philosophers like Ibn Baha, Ibn Tufla, al-Bidarji, Averroes, and Maimonides questioned the traditional theories of their time. During this period, astronomical observatories were established in Islamic countries, including Moraga, Tabriz, Ulagbek in Samarkand, and Istanbul. Additionally, there were madrasas where astronomical education was provided. The Moraga revolution is a theory of planetary motion that denies the equant and other elements of Ptolemy's theory as the foundation of mathematical astronomy, which was developed by scientists such as Nasr al-Din al-Tusi, Qutb al-Din al-Shirazi, Muayyad al-Din al-Urdi, Muhammad ibn al-Shatir, a broad discussion of the natural philosophical foundation of astronomy and the possibility of rotating the Earth around its axis. Science in Islamic countries continued to develop until the middle of the 16th century when major astronomers worked. Taqiyuddin al-Shami, al-Burjandi. Although qualified researchers met at a later time, since the end of this century, a long era of stagnation has begun in Islamic science. Historians have yet to figure out the reasons for the centuries-old stagnation in the science of Muslim countries. The significance of astronomy for the future development of science in Islamic countries is significant. Arabic astronomy played a crucial role in the development of celestial science. Scientists from the Islamic world improved a number of astronomical instruments and created new ones, significantly enhancing the accuracy of measuring various astronomical parameters. Without these advancements, the further development of astronomy would have been challenging. Moreover, it was these scientists who first proposed the fundamental idea that astronomical theory is an integral part of physics. This breakthrough paved the way for further exploration and understanding of the universe. Of Europe in the 13th and 15th centuries developed under the influence of a combination of the traditions of medieval astronomy with the influence of Arab scientific achievements transferred to Europe. During this period, European astronomers were mainly engaged in observing the apparent movements of the planets, coordinating them with the accepted geocentric system of Ptolemy. In the 13th century in Spain, the Castilian king Alfonso X built an astronomical observatory near Toledo, where tables based on the Ptolemaic system were compiled. They surpassed the previous ones in accuracy and became widespread in Europe. John de Sacrobosco is an astronomer, mathematician, and calendar calculus specialist. The author of the essay on the sphere, which contains evidence of the spherical shape of the Earth and describes the basic astronomical concepts. Regiomontanus is a German astronomer, mathematician, and astrologer. He founded an astronomical observatory in Nuremberg, compiled tables ephemerides with the positions of the Sun, Moon, and planets. Since the 15th century, the rise of scientific thought in European astronomy began, associated with the development of the heliocentric system of the world and the discovery of the laws of motion of celestial bodies. An important role was played by the works of scientists Georg Purbach and Johann Müller-Regiomontan, who became convinced that astronomical tables were outdated. Regiomontanus compiled new tables of sines and tangents, which became the main astronomical guides for Europeans. Astronomers collected data on the movements of celestial bodies, built angle measuring instruments triquetrams, quadrants. The sailors, traveling from the northern hemisphere to the southern hemisphere, observed the change of constellations that can be visible at different latitudes, and were convinced by their own experience of the spherical shape of the Earth. Nicolaus Copernicus is a Polish astronomer, the author of the heliocentric system of the world. The Sun is the center of the solar system, and the Earth revolves around it. Johannes Kepler is a German astronomer who established the laws of planetary motion. Tycho Brahe is a Danish astronomer who was the first in Europe to conduct systematic and highly accurate astronomical observations. Galileo Galilei is an Italian scientist, physicist, mathematician, and astronomer, one of the founders of natural science. Using an improved telescope, he discovered craters on the Moon, sunspots, and rings of Saturn, and traced the phases of Venus. In the 16th and 18th centuries, significant changes took place in European astronomy, associated with the emergence of new ideas and ideas about the world around us, as well as the improvement of observation techniques. Formulation of the law of universal gravitation. Isaac Newton published a law that explained how celestial bodies interact and made it possible to more accurately predict the movements of planets and comets. Edmund Halley calculated the orbits of more than 20 comets and noted that several of their appearances refer to the same comet named after him. In 1718, the scientist Halley discovered a large displacement of the three brightest stars, Sirius, Arcturus, and Aldebaran. This is how the proper motions of the stars were discovered, and they were no longer considered stationary. Determination of the average distance from the Earth to the Sun astronomical unit. The first close-to-true results were obtained by the Halley method from observations from different places of the transit of Venus across the Sun's disk in 1761 and 1769. Leonhard Euler is a Swiss, Prussian, and Russian mathematician, physicist, mechanic, and astronomer. He discovered an equation that makes it possible to determine the basic parameters of a comet's parabolic orbit and built the first theory of motion of planets and comets based on Newtonian gravity. Joseph Jerome Lefrancois de Lalande is a French astronomer and mathematician. He clarified the lunar parallax, taking into account the non-spherical nature of the Earth, calculated the exact time of the first predicted return of Halley's comet in 1759, organized observations of the transit of Venus across the Sun's disk in 1769 and processed the data from these observations. 1784. J. Goodrake suggested that Algol's variable brightness is caused by eclipses from another component of this binary star. Surveillance tools. Telescopes with achromatic lenses, they compensated for the effect of chromatic aberration, gave a large field of view in sharp images. The passage instrument was a telescope with a horizontal axis, a lens, and an eyepiece, which made it possible to observe the moments of a star passing through a point. The mirror quadrant is a tool for determining the height of the sun above the horizon when viewed from a ship. Astronomy of the 19th century became a time of rapid development of astronomical science and celestial mechanics. The number of observatories in Europe increased. The size of the telescopes also grew, so in 1845 the 2-meter Leviathan reflector came into operation. In 1861, William Lassells built a 120 cm reflector. On January 1, 1801, the Italian Giuseppe Piazzi discovered Ceres. Located in the asteroid belt, it was spotted by chance, classified as a comet, and immediately lost. Fortunately, at that time the young Carl Gauss developed a method for determining the orbit from 3 observations. And in 1802 Heinrich Olbers first found Ceres and then discovered 2 more minor planets between Mars and Jupiter, Pallas in 1802 and Vesta in 1807. The 4th asteroid, Juno, was discovered by Karl Harding, Germany in 1804. Heinrich Olbers put forward the first hypothesis about the causes of the formation of the asteroid belt. By the end of the century, up to 400 of them were discovered. The term asteroids was proposed by Herschel. Asterisk 1802, William Hyde Wollaston invents the slit spectroscope. 7 dark lines have been detected in the spectrum of the Sun. 1811, Dominique Arago invents the polarimeter and uses it to prove that the solar photosphere is an incandescent gas. Many scientists still consider the body of the Sun to be solid and even cold. 1814 to 1815, Joseph Fraunhofer discovers 576 dark lines in the spectrum of the Sun. The laboratory sodium line coincided with the dark solar line. Spectral analysis soon appears. 1834, German astronomer Friedrich Wilhelm Bessel proves the absence of an atmosphere on the Moon. There is no refraction at the edge of the lunar disk. 1839 to 1840, photography begins to be used in astronomy. 1843, Heinrich Schwab was the first to discover the periodicity in the change in the number of sunspots and estimated the period at about 10 years. 1845, the giant reflector of the Irish astronomer William Parsons, Earl of Rosse, came into operation. Herschel's mistake was immediately revealed. Most of the planetary nebulae turned out to be star clusters. 1846, the triumph of Newtonian mechanics was the discovery of Neptune, the 8th planet of the solar system, discovered at the tip of a pen. Almost immediately, William Lassells discovers Neptune's moon, Triton. 1851 to 1852, laboratory measurement of the speed of light. 1857, the exact scale of stellar magnitudes. 1859, James Clerk Maxwell established the meteoritic structure of Saturn's ring. 1859 to 1862, Kirchhoff and Bunsen developed a powerful method for remote investigation of the chemical composition of extraterrestrial objects, spectral analysis. As early as 1861, Kirchhoff published a preliminary chemical composition of the solar atmosphere. 1862, Arthur Charles Clarke discovered the satellite star of Sirius B, predicted by Bessel. 1868, Joseph Norman Lockyer discovered a line in the spectrum of the Sun that did not correspond to any of the chemical elements known at that time and named this new element helium. Later, helium was found on Earth. In 1873, he suggested that the decomposition of chemical elements takes place in the depths of the Sun. 1877, a soft hole discovers the moons of Mars Phobos and Deimos, and Giovanni Schiaparelli discovers the Martian channels. 1879, George Howard Darwin publishes the hypothesis of the tidal origin of the Moon. 1885, the first observation of a nova flare in the Andromeda Nebula S. Andromeda. Later, it turned out that it was a supernova. 1898, William Henry Pickering discovers Phoebe, a moon of Saturn, and its amazing feature is its reverse rotation relative to its planet. The 20th century began with the continuation of new discoveries in astronomy. 1902, Albert Michelson clarifies the speed of light to 199,890 plus or minus 60 kilometers per second. 1908, a magnetic field was discovered near the Sun. 1908 to 1916, the discovery of a directly proportional relationship between the period and the apparent magnitude of the Cepheids in the Small Magellanic Cloud. 1912, the discovery of cosmic rays. 1913, unusually large redshifts were discovered in spiral nebulae. 1914 to 1919, the theory of Cepheid pulsation by Harlow Shapley and Arthur Eddington. 1916, Barnard's flying star was discovered. 1916 to 1918, theory of the internal structure of stars. 1918, Harlow Shapley's model of the structure of the galaxy, derived from observations the diameter and position of the center were correctly determined unexpectedly. It turned out that the Sun was located on the edge of the galaxy. 1923, the discovery of the 22-year cycle of the Sun's magnetic activity and the reversal of the sunspot's polarity. 1924 to 1926, the theory of radiant equilibrium of the stellar interior by Arthur Eddington. 1925 to 1934, the discovery of carbon dioxide on Venus. 1926 to 1927, based on the analysis of the motion of stars, Bertil Lindblad and Jan Oort established the rotation of the galaxy. 1927, Georges Lemaître publishes his hypothesis of the expansion of the universe. 1929, Hubble's law was established. 1930, on February 19th, Pluto was discovered by Clyde Tombaugh. 1931, Arthur Millen's hypothesis, a white dwarf remains after the nova explosion. Early 1930s, Fritz Zwicky concludes that there is a hidden mass in the universe. 1934, Pavel Paranago and Boris Kakarkin predict the outburst of the star T of the northern corona. It really happened in 1946. 1934, Walter Pora and Fritz Zwicky suggest that a neutron star remains after a supernova explosion. 1942, Mayol and Jan Oort discover that the Crab Nebula is a remnant from the supernova explosion of 1054. The first radio map of the sky has been compiled. 1945, the redshift was confirmed in the radio range. 1950, Oort's hypothesis about the existence of a spherical layer of comets at the edge of the solar system, the Oort cloud. 1951, the spiral structure of our galaxy was proved. 1955-1956, registration of radio emissions from Venus, Jupiter, and comet Aran-Trolong. 1957, the launch of the first artificial satellite of the Earth, Sputnik 1, the beginning of the space age. It became possible to create space laboratories. Since 1957, the era of space research began in astronomy, which made it possible to study celestial bodies and the space environment using artificial devices. In the next video, we'll look at how the first artificial satellite was launched. See you among the stars? Watch my channel and subscribe. You will learn a lot of new and interesting things. Click on the bell to be the first to watch new videos on the channel.